Good day everyone. Today we're going to learn more about soil chemistry that will be presented by Denise Pambuan, Ira Marie Elumba, John Paul Morales, Mark Joseph Osmilio, and Kiana Laureen Sunico. Introduction to soil chemistry. Soil is at the top or outer layer of our Earth's crust that covers most of the land and is the natural medium for the growth of plants. Soil is also a complex mixture of minerals, organic matter, water, air, and living organisms. It provides the structural support to plants used in agriculture and is also their source of water and nutrients. Next we have benefits of soil. First, we have food security, which soil is the backbone of our food security that 95% of our global food production relies on soil. Next, we have ecosystem services, where soil helps us to filter and purify water as it moves through the ground, removing pollutants and other contaminants. This helps to ensure that we have access to clean drinking water. Soil is also a nutrient giver and a home to wide range of plants and animal species that makes up a diverse ecosystem. Are also an important source of medicine, such as antibiotics like penicillin, which is produced by a fungus, along with streptomycin, chloramphenicol, and tetracycline, which are produced by a soil bacteria. Next, we have climate change. Soil prevents floods by transferring water slowly to the streams and groundwater. It also stores carbon dioxide and other greenhouse gases in the soil organic matter. Therefore, it helps us to regulate the climate change. Moving on to the soil chemistry. Soil chemistry is the study of chemical properties and processes that occur within soils. Soil chemistry plays a critical role, especially in managing soil health, supporting agriculture, protecting the environment, and promoting sustainability. It includes the analysis of composition of the soil pH, and the interaction between the soil components such as mineral, organic matter, water, and air. Soil composition. In the soil composition, we have the ingredients of soil. The solid materials are further divided into mineral matter and organic matter, while the pore spaces are made up of air and water. In general, the soil contains 40 to 45% of mineral matter, 5% of organic matter, 25% of soil water, and another 25% of soil air. In order to sustain a plant life, it needs a proper mix of air, water, minerals, and organic minerals. So there are four major components of the soil. First, we have the mineral matter. It constitutes about 45% of the total soil composition. It is made up of a number of particles which vary in size, shape, and chemical composition. Along with soil organic matter, it makes up the solid material phase of the soil. Generally, mineral matter is divided into sand, silt, and clay, which are often considered as the main mineral particles. All the constituents of the mineral matter are products of weathering, and as such, they share a common origin, the massive soil-forming rocks. They are therefore mineral in nature. There are two types of minerals, the primary and the secondary. The primary minerals are products of accelerated physical weathering, and they are often bigger and coarser texture. Primary minerals are gravel, sand, and some of silt. On the other hand, the secondary minerals do not bear any resemblance to the original material. as they do not retain the structure, properties, or composition of the original mineral. Secondary minerals are the products of chemical weathering and are often smaller and of a finer texture. Secondary minerals make up of clays and some of the silt. Next is the organic matter. Organic matter is the next basic component that is found in soils at the levels of approximately 1% to 5%. Soil organic matter is the fraction of soil that consists of plants or dead or animal tissues in various stages of breakdown, or what we call decomposition. Organic matter is derived from dead plants and animals, and as such has a high capacity to hold onto or provide the essential elements and water for plant growth. The organic material of soil, called humus, is made up of microorganisms, dead and alive, and dead animals and plants in varying stages of decay. Humus improves soil structure, providing plants with water and minerals. Next is the soil water, a part of the soil volume that is not occupied by the soil particles, known as pore spaces, that is filled partly with soil water and partly with soil air. Soil water competes with soil air for the pore spaces in the soil, hence it moves in as air moves out. Soil water is the major component of the soil in relation to plant growth. Water is about 25% of the soil volume. It is important for transporting nutrients to growing plants and soil organisms. As a universal solvent, it creates a solution by dissolving nutrient elements, thus making them available for plant use. Lastly, we have soil air. The soil air is about 25% of the soil volume. It occupies those pore spaces not occupied by soil water. The volume of air in the soil depends on only one factor, which is the volume of water present in the soil. Therefore, the more the water a soil has, the less air it will have, vice versa. The major source of soil air is mostly is the atmosphere above the soil. Soil air contains a much greater proportion of carbon dioxide and a lesser amount of oxygen than the atmospheric air. There is oxygen that is essential for the root and microbe respiration, which help support the plant growth, while carbon dioxide and nitrogen are also important for below ground function, such as nitrogen fixing bacteria. If soils remain waterlogged, where gas is displaced by excess water, it can prevent root gas exchange, leading to plant death, which is a common concern after floods.
And now, we will talk about the difference between soil organic matter and inorganic matter. For soil organic matter, it is any material produced originally by living organisms, whether it is a plant or animal, that is returned to the soil and goes through the decomposition process. At any given time, it consists of a range of materials, from the intact original tissues of plants and animals to the substantially decomposed mixture of materials known as humus. This serves as a reservoir of nutrients for crops, provides soil aggregation, increases nutrient exchange, retains moisture, reduces compaction, reduces surface crusting, and increases water infiltration into the soil. Organic matter is made up of different components that can be grouped into three major types. First, we have fresh plant residues and living microbial biomass. For fresh plant residues, it refers to a plant residue, animal, or other organic substances that have recently been added to the soil and have only begun to show signs of decay. It does not include surface residue cover. For living microbial biomass, these are made up of bacteria, fungi, nematodes, protozoa, arthropods, and etc. Next, we have active soil organic matter, also referred to as detritus or decomposing. Microorganisms and other organic compounds are used as food by microorganisms. Active soil organic matter decomposes faster than other components of soil organic matter in response to management changes. Lastly, we have stable soil organic matter, often referred to as humus. It is the product of microbial decomposition, dark-colored, dynamic substances composed of residual organic matters not readily decomposed by soil microorganisms. Humus improves soil structure, providing plants with water and minerals. The process of humus formation is called humification. Components vary in proportion and have many intermediate stages. Plant residues on the soil surface, such as leaves, manure, or crop residue, are not considered SOM, or soil organic matter, and are usually removed from soil samples by sieving through a 2 mm wire mesh before analysis. Increasing levels of organic matter improve the physical, chemical, and biological functions of the soil. The benefits of organic matter are: first, biological function. There are many benefits to organic matter, most of which begin with enhancing the biological diversity and activity in the soil. As organic matter increases, microbial activity tends to increase. Organic matter consists of 58% carbon, which is required in combination with other nutrients for microbial activity. Microorganisms excrete compounds that also act as a binding agent for soil particles, which can increase aggregate stability, water infiltration, and water holding capacity. Next, we have nutrient supply. Organic matter is a valuable nutrient source for plants and living organisms. As microorganisms increase their activity during warmer weather that occurs predominantly in the spring and summer, greater amounts of nutrients are cycled from organic forms into those that are inorganic and plant available. Next is soil structure. Organic matter causes soil particles to bind and form stable soil aggregates, which improves soil structure. With better soil structure, water infiltration through the soil increases and improves the soil's ability to absorb and hold water, as well as reduces the potential for surface crusting of the soil. Next is water holding capacity. Soils with higher organic matter can infiltrate and store water at greater capacities. Organic matter behaves similar to a sponge, with the ability to absorb and hold up to 90% of its weight in water. A great advantage of the water holding capacity of organic matter is that it will release most of the water that it absorbs. Last is the erosion control. Greater aggregate stability is often the result of soils with more organic matter. which can increase water infiltration rates and result in reduced potential for water, soil, and nutrients to erode. Data used in the Universal Soil-less equation indicate that increasing soil of organic matter from 1 to 3% can reduce erosion 20 to 33% because of increased water infiltration and stable soil aggregate formation. Next is soil inorganic matter or soil mineral. The inorganic material of soil is composed of rock, slowly broken down into smaller particles that vary in size. The following are soil particles that are 0.1 to 2 mm in diameter are called sand. Soil particles between 0.002 and 0.1 mm are called silt. And also even smaller particles less than 0.002 mm in diameter are called clay. Most soils have some of each. Soils with a large proportion of each component are called loams. The most common minerals found in soil are phosphorus, potassium, and nitrogen gas. Other, less common minerals include calcium, magnesium, and sulfur. For the components of inorganic material, first, we have the sand. Sand is a medium to coarse-grained sediment that is visible to the naked eye. It consists of pieces of weathered rock such as quartz, magnetite, or other mineral or shell fragments. Sand in your garden soil will help promote good drainage and aeration of the area. However, sand alone will not retain significant amounts of moisture to support plant growth. In addition, sand does not contain nutrients that promote healthy plants. Next is silt. Silt is a fine-grained sediment that you cannot see with the naked eye. Silt is larger than clay and smaller than sand and may feel gritty between your fingers. Like sand, silt results from the weathering of rocks and consists of grains of quartz, feldspar, and other minerals. Silt-rich soil will retain moisture for plant growth, but at times, it can limit drainage and make the soil difficult to till. Silt itself does not contain plant nutrients. However, existing nutrients in the area may adhere to the surface of the silt particles in the garden soil. Last one is clay. Clay is another fine-grained sediment that is smaller than silt. Minerals such as feldspars degrade over time to form clay. Like silt, clay-rich soil will retain moisture for plant growth and may limit drainage in the area. Unlike sand and silt, the aluminum silicate minerals that degrade to clay will provide important plant nutrients such as iron, calcium, magnesium, and potassium. Existing nutrients will cling to the clay soil particles and help to feed plant growth in the root area. Now let's move on to soil degradation. Soil degradation is the decline in soil condition caused by its improper use or poor management, usually for agricultural, industrial, or urban purposes. It is a serious environmental problem. It can be the loss of organic matter, decline in soil fertility and structural condition, erosion, adverse changes in salinity, acidity, or alkalinity, and the effects of toxic chemicals, pollutants, or excessive flooding. Unfortunately, many human activities degrade and pollute soils, lessening the ecosystem, services provided by soils, and making some soils and their runoff water harmful to our environment and human health. Soil degradation can involve erosion, salinization, and desertification. For erosion, It is among the great causes of soil degradation, as essential topsoil is lost at rates far greater than it can be replaced. This sediment is also among the greatest pollutants of water bodies. Salinization and desertification are major causes of soil degradation in arid areas. Salinization is the buildup of salts in soils to a point that they destroy the physical and chemical properties of soil and make it impossible for plants to take up water from the soil. Salinization is often associated with improper irrigation, while desertification is caused by combination of climate changes and human-induced soil degradation such as through overgrazing. Soil degradation can be worsened by climate change. Dry areas are generally becoming drier due to climate change, making these areas more vulnerable to soil degradation.
First in the soil properties is colors. The colors of the soil is usually the first thing people notice. It can offer information on the composition, organic matter content, and drainage of the soil, the amount and kind of minerals and organic matter present in the soil, as well as the degree of soil growth and the amount of water available, all influence soil color. This is mostly topsoil, although it does not represent the complete soil. Since organic matter accumulates in the topsoil, it is frequently darker than the lower layers or horizon. A standard color chart, such as the Munsell soil color chart, is used to characterize soil color. The chart uses the three characteristics to define soil color: hue, value, and chroma. The primary color of the soil, such as red, yellow, or brown, is referred to as its hue. The brightness of a color ranging from black to white is referred to as its value. The intensity of saturation of color, ranging from drab to dazzling, is referred to as chroma. The color of soil can vary widely based on its location and climatic circumstances. Soils in dry locations, for example, have a lighter hue owing to a lack organic matter and the presence of calcium carbonate, whereas soils in humid regions have a deeper color due to the presence of organic matter. So there are 6 types of colors of a soil. The first one is a black color of soil from organic matter, and the characteristic of this color of soil is often associated with high levels of organic matter or pits. The second one is the white or pale, or we can call it as a bleach color soil. These soil are referred to as bleach or washout. The iron and manganese particles have been leached out due to high amounts of rainfall or drainage. Next is red. It's from iron and aluminum oxides. These colors indicate good drainage. Iron found within the soil is oxidized more readily due to the higher oxygen content. This causes the soil to develop a rusty color. The color can be darker due to the organic matter. The next one is the yellow to yellow brown. This color of soil has a poorer drainage than the red soil. The iron compounds in these soils are in a hydrated form, and therefore they do not produce the rusty color. The fifth one is the brown. This color has an organic matter level and iron oxide. Brown soils are well drained and may be found in a wide range of climates from humid to desert. They are commonly found in locations with moderate rainfall and temperature, and can be generated from a range of parent materials such as sedimentary rock, glacial till, and alluvial deposits. And the last one is glade or green or gray color. This color of soil has a very poor drainage or watering. The lack of air in these soils provide conditions for iron and manganese to form compounds that give these soils their color. Knowing soil color is crucial in agriculture because it affects soil suitability for different crops as well as the management measure required to maintain soil fertility and avoid erosion. Soil color can also influence landscape aesthetic and soil suitability for building or engineering tasks. Ultimately, soil color is only one of many significant aspects to consider when analyzing and managing soils, but it may give useful information about soil features and qualities. Next is soil texture. Soil texture is a classification instrument used both in field and laboratory to determine soil classes based on their physical texture. Soil texture such as loam, sandy loam, or clay refers to the proportion of sand, silt, and clay-sized particles that make up the mineral fraction of the soil. For example, light soils refer to a soil high in sand relative to clay, while heavy soils are made up of largely of clay. Texture is important because it influences the amount of water the soil can hold, the rate of water movement through the soil, and the third one is how workable and fertile soil is. There are several methods for classifying soil texture, but the common is based on the relative quantities of sand, silt, and clay particles in the soil. Soil can be classified into 12 major texture classes. First is sand. Sand is a soil texture that consists of mostly large particles and has a diameter ranging from 0 to 0.5 millimeter to 2 millimeter. Sand particles may be seen with the naked eye and have a gritty sensation when brushed between the fingertips. Sand soils are well drained and have a limited water holding capacity, which means they do not keep water for an extended length of time. Next is loamy sand. It's a soil texture that is intermediate between sand and sandy loam. It is made up of approximately 70 to 90% and sand and 0 to 50% silt and 0 to 10% clay particles. The texture of loamy sand soils is gritty with some finer particles that give the soil a somewhat smoother feel than pure sand. Next is fine sandy loam. It's a soil texture that is intermediate between sandy loam and loam. It is made up of 50 to 70% of sand and 20 to 30% of silt and fewer than 20% of clay particles. Fine sandy loam soils have a granule texture with visible sand grains and finer particles that provide a smoother feel than sandy loam soils. Next is loam, composed of equal parts of sand, silt, and clay particles. Typically, 20 to 40% of each is used. Loam soils have a granule texture with visible sand grains, silt particles, and tiny clay particles, giving the soil a slightly sticky feel. Next is silt loam. It's a soil texture that is between loam and silty clay loam. It is made up of 80 to 90% of silt, 0 to 20% of sand, and 0 to 10% of clay particles. Silt loam soils have a smooth texture with no visible sand grains and only a few tiny clay particles that add a somewhat sticky feels to the soil. Next is sandy clay loam soil texture that is between sandy loam and clay loam. It is made up of 50 to 70% of sand, 20 to 30% of clay, and 0 to 20% of silt particles. Sandy clay loams soils have a gritty texture with visible sand grains and clay particles that make the soil slightly sticky. Next is silty clay loam. Silty clay loam soil texture that is between clay loam and silty clay. It is made up of 62% silt and 10 to 25% of clay and 0 to 20% of sand particles. The texture of silty clay loam soil is smooth with no visible sand grains and modest number of microscopic clay particles that give the soil is somewhat sticky feel. Next is clay loam soil, texture that is between clay and sandy clay. It is made up of 20% to 45% of clay, 30% to 50% of silt, and 10% to 30% of sand particles. Clay loam soils have a smooth texture with visible sand grains and tiny clay particles, giving the soil a slightly sticky feel. Next is sandy clay soil texture that contains a higher proportion of sand particles than clay particles. Nonetheless, there is enough clay in the soil to give it slightly sticky texture. Sandy clay is made up to 20 to 35% of clay and 45 to 65% of sand and 10 to 30% of silt particles. Next is silty clay. Silty clay soil is a soil texture that comprises more silt particles than clay particles. Nonetheless, there is enough clay in the soil to give it a smooth, somewhat sticky texture. Silty clay is made up of 40% to 60% of clay and 20 to 40% of silt and 0 to 20% of sand particles. And the last one is a clay. Clay is a soil texture with a high concentration of clay particles which gives the soil a smooth sticky feel. Clay is made up of at least 40% of clay particles, 20 to 45% of silt particles, and 0 to 45 sand particles.
So the next property is the layers of soil. It is made up of 5 distinct layers, which are collectively known as soil horizons. Each of these layers has distinct properties that have an important role in defining the soil's health and fertility. There are generally 5 different layers or horizons of soil: the O horizon, A horizon, E horizon, B horizon, and the C horizon. So the one on which we stand is called the O horizon, or the organic layer, or also called as the humus layer. It is composed of decayed plant debris such as leaves, twigs, and other organic materials and form humus. This tells us how fertile the soil can be. Based on the soil type, it may be thick, thin, or completely absent. This layer is critical for plant development and is often extremely nutrient dense. The O horizon is rich in organic materials and has a loose, spongy texture. Because of the high concentration of humus, a dark-colored substance created by the breakdown of organic materials, it is generally dark in color. The type of vegetation existing in the region can also impact the texture of the O horizon, as various species of plants create different forms of organic debris. Just below is the A horizon, or also called the topsoil, which is typically the most fertile layer of soil, and it contains a mix of organic and mineral material, and it is typically dark in color. This is where we plant our seeds so they can grow to be strong and healthy plants. This is because it is rich in minerals and humus. It is soft and porous so that the plants can stretch its roots. Porous meaning having minute spaces or holes through which liquid or air may pass. The A horizon or topsoil is considered the home of worms and rodents because it has a high concentration of organic materials, which offers a nutrient-rich habitat for these species to live. Worms play a crucial part in the soil ecosystem by consuming and decomposing organic matter, which aids in the release of nutrients and minerals required for plant development. Rodents, on the other hand, have the ability to dig and tunnel through soil, aerating it and assisting in the mixing of nutrient and organic materials across the soil layer. Worms and rodents are key makers of soil health, and their presence in the topsoil layer is often seen as a positive signal of a healthy and fertile soil. Below the A horizon is the E horizon or the alluviation layer. The E horizon is a lighter colored soil layer that sits beneath the A horizon where organic materials, clay, or both have washed out of the layers, generally giving it a lighter color and an ashy or chalky sensation to touch. The texture is typically comparable to the horizon above it, although it contains less clay than the horizon below it. Water penetrates through the soil, taking nutrients and minerals with it, forming this layer. Therefore, as the water moves down the soil, substances are removed and pools pulled out from this layer, resulting in a concentration of sand silt particles. This layer may be missing in some soils. Below is the B horizon or the subsoil. The B horizon or subsoil is composed of thicker clay and mineral deposits like iron, aluminum oxides, and calcium carbonate, and is less fruitful than the topsoil. Since it is where elements leach from the topsoil tend to concentrate over time, this layer is commonly referred to as the zone of accumulation. It may also contain sand or gravel, and it frequently has a lower organic content than the layers above it. It is hard and compact, so only the roots of big and strong plants can reach this horizon. The B horizon's texture and content are important indicators of soil health and fertility. Soils with a healthy B horizon can better support plant development and other soil activities by providing a strong foundation for roots and holding onto water and nutrients. Soil scientists frequently measure soil quality and fertility by examining the texture and content of the B horizon. The fifth horizon is the C horizon or the regolith. The C horizon is the layer of soil closest to the bedrock underneath. It is composed of weathered rock pieces and other mineral deposits and often contains the least biological content. It is the deepest layer of soil and is sometimes referred to as the parent material since it is the layer from which the other soil layers have grown through time. This horizon is an important layer in soil development because it allows roots to penetrate and store nutrients. It also functions as a water reservoir, which is necessary for plant development and survival. But nonetheless, because it serves as the basis for the other soil layers, the texture and composition of the C horizon can have a considerable influence on the overall health and fertility of the soil. In addition to these 5 primary layers, some soils might also have R horizon or bedrock. This is the hardest layer and consists of unweathered parent rock which supports all layers above it. Each soil layer's thickness and composition can vary greatly based on factors such as climate, topography, and local geology. Whereas, R horizon is not technically soil, but it can have an effect on the soils above it. The type of rock that makes up the R horizon can have an impact on the soil's nutrient content and general fertility. Soils developed from limestone bedrock, for example, could be more alkaline and have greater quantities of calcium, whereas soils formed from granite bedrock may be more acidic and contain lower levels of nutrients such as phosphorus and potassium. The R horizon is typically not accessible to plant roots and therefore does not play a direct role in supporting plant growth. However, the underlying bedrock can have a significant impact on soil development and fertility over time, as it is weathered and broken down into smaller particles that makes up the upper soil horizon. So next, we have the soil structure. Soil structure is defined by the way individual particles of sand, silt, and clay are assembled. Single particles, when assembled, appears as larger particles. These are called aggregates. Soil structure is significant because it influences several elements of soil behavior such as water transport, aeration, nutrient availability, and plant root development. Soil structure is the arrangement of sand, silt, and clay particles in a soil. So now, we have here the different types of soil structure: the granular, blocky, prismatic, platy, and columnar. The first one, we have the granular soil structure, or also known as crumb structure. It is a kind of soil structure distinguished by tiny, spherical soil particles that combine to create loosely packed, and crumbly aggregates. These aggregates have a granular appearance and are generally 1 to 10 millimeters in diameter. Individual particles of sand, silt, and clay are clustered together in tiny, almost spherical grains to form granular and crumb structures. Water quickly circulates through such soils. They are the most typically found in the soil profiles A horizon. Granular soil structure may be found in many different types of soil, including sandy loam, and silt loam. It is regarded as the most desired form of agricultural soil structure since it provides for good root penetration, water, and nutrient retention, and overall plant growth. The next structure is the blocky structure. In blocky structure, the structural units are block-like or polyhedral. They are bounded by flat or slightly rounded surfaces that are casts of the faces of the surrounding beds. Typically, block structural units are nearly equidimensional but grade to prisms and to plates. Relatively large blocks indicate that the soil resists penetration and movement of water. This structure is common in clay soils and is often found in subsoils. There are two types of blocky structure. The structure is described as angular blocky if the faces intersect at relatively sharp angles, and subangular blocky if the faces are a mixture of rounded and plane faces and the corners are mostly rounded. So blocky structures are common in subsoil but also occur in surface solid that have a high clay content. The strongest blocky structure is formed as a result of swelling and shrinking of the clay minerals which produce cracks. Sometimes, the surface of dried up sloughs and ponds shows characteristics cracking and peeling due to clays. Next is the prismatic structure. Prismatic structure is a type of soil structure that is characterized by the formation of vertical columns or pillars within the soil. These columns can be several centimeters in diameter and extend down through multiple soil layers. This structure is typically found in soils that have a high concentration of clay materials or clay minerals, as well as soils that have undergone significant shrink-swell processes. The formation of prismatic structure is thought to occur when clay particles in the soil swell with water and then shrink as the soil dries out, causing the soil to crack and form columns. The vertical cracks result from freezing and thawing and wetting, drying, as well as the downward movement of water and roots. Over time, these columns can become more defined and stable, creating a distinct prismatic structure. Prismatic structure can have both positive and negative effects on soil health and fertility. On the one hand, the vertical columns can provide channels for water and air to move through the soil, which can improve soil drainage and aeration. Additionally, the presence of prismatic structure can help to stabilize the soil, reducing the risk of soil erosion. However, prismatic structure can also have negative effects on soil health. For example, the vertical columns can limit the movement of roots through the soil, which can impact plant growth and nutrient uptake. Additionally, prismatic structure can make it more difficult for water to infiltrate the soil, which can lead to waterlogging and other drainage issues. The next one is the platy structure. The components of a platy structure are flat and plate-like. They are typically horizontally oriented. For plates that are thickest in the center and thinnest at the edges, lenticular platy structure is identified. Platy soil structure is formed when soil particles are compacted and flattened, resulting in the formation of horizontal layers. This can occur naturally over time due to soil erosion, or it can be caused by human activities such as heavy equipment use or overgrazing. The structure impedes water infiltration and drainage leading to poor soil aeration and low plant productivity. The plates may be easily detached by pulling the horizontal layers apart with a penknife. The platy structure of the soil tends to obstruct the downward circulation of water and plant roots. Platy structure is commonly found in clay soils, particularly in the subsoil layers. In order to improve the structure and fertility of platy soils, it is important to reduce compaction through practices such as deep tillage, cover cropping, and soil amendment with organic matter. These practices can help to break up the compacted layers and promote the development of more favorable soil structure. Lastly, the columnar structure. The units of a columnar structure are comparable to prisms, with flat or slightly rounded vertical sides. In contrast to prisms, the tops of columns are distinct and typically rounded. Columnar structure is frequent in sodium-affected soils. The columnar structure is extremely thick, making it difficult for plant roots to penetrate these layers. Deep plowing, for example, has helped to restore some fertility to these soils. Columnar soil structure is formed when soil particles are cemented together by minerals such as calcium carbonate or sodium carbonate. As the soil dries out, shrinkage causes the soil to crack and form column-like aggregates. When the soil becomes wet again, the cracks fill the water and the aggregates expand, leading to the formation of a honeycomb-like pattern. Columnar soil structure can be both beneficial and problematic for plant growth. On the one hand, the structure allows for good water infiltration and drainage, making it favorable for some crops. On the other hand, the structure can create a dense, impermeable layer at the bottom of the columns, limiting root growth and nutrient uptake.
Now, we proceed to the soil pH. Soil pH is a measure of acidity or alkalinity of the soil. A pH value is actually a measure of hydrogen ion concentration. Because hydrogen ion concentration varies over a wide range, a logarithmic scale is used for pH decrease of 1 and acidity increases by a factor of 10. Its reverse scale in the a very acid soil has a low pH and a hydrogen ion concentration. Therefore, at high alkaline pH values, that hydrogen ion concentration is low. Most soils pH have a value between 3.5 and 10. In the higher rainfall areas, the natural pH of soils typically ranges from 5 to 7, while in drier areas, the range is 6.5 to 9. Now, we proceed to the factors of soil pH. First is acidity. This process tends to cause a lowering of pH and increasing the acidity over time. Acidic soil tend to be high in iron and aluminum oxide, as they are the slowest minerals to weather in soil. Aluminum in these increasingly acidic soils is solubilized and will combine with the water to release additional hydrogen ions, contributing to further acidity. Soils in areas with a large amounts of rainfall tend to acidic because of the water leaches basic oceans such as calcium, magnesium, potassium, and sodium out of a soil profile, leaving room for acidic oceans such as hydrogen and aluminum. The parent substrate from which of the soil developed can be source of acidity. For instance, soil developed from the land with organic matter containing conifers or with the high contents of iron or aluminum tend to be acidic. Acidity can also increase by several additional factors, including the nitrification of ammonium fertilizers, which yields hydrogen ions. The next factor is alkalinity. Alkalinity soils become alkaline for a variety of reasons. They may be located on very dry and with a little rainfall areas. The alkalinity might be caused by the nature of the soil itself, or other result of receiving water to the contains highly alkaline substances such as calcium or magnesium carbonate. Next is the effects of soil pH. Soil pH affects the amount of nutrients and chemicals that are soluble in soil water, and therefore the amount of nutrients available to plants. Some nutrients are more available under acid conditions, while others are more available under alkaline conditions. However, most mineral nutrients are readily available to plants when soil pH is near neutral. The development of strongly acidic soils less than 5.5 pH can result in poor plant growth as a result of one or more of the following factors. This is the following factors: aluminum toxicity, manganese toxicity, calcium deficiency, magnesium deficiency, low level of essential plant nutrients such as phosphorus and molybdenum. Alkaline soils may have problems with deficiencies of nutrients such as zinc, copper, boron, and manganese. Soils with extremely alkaline pH greater than 9 are likely to have a level of sodium. The correct balance is where the soil pH is between 5.5 and 7.5. So every effort should be taken to check soil pH level regularly. Early identification of soil pH problems is important as it can be both costly and difficult to correct long-term nutrients deficiency.